In this video, we're looking at section 2.3 in the textbook, and we're looking at intervals on which a function increases, decreases, or is a constant. So we're looking at interpreting graphs. First of all, whenever you read a graph, you always read it left to right, just like you were reading text in a book. To decide whether a function is increasing, decreasing, or is constant, it depends on which way the graph is, what direction the graph is going, moving from left to right. So let's show an example. Let me just sketch a simple graph here with positive x and y axes. And if I were to draw a line this way, and to read it, I'm going to just grab a line here, a vertical line that I can move. Oops, over here that doesn't work right. Here we go. There we go. So if we're going to read this graph left to right this way, you'll notice that the direction of the line is going up to the right. So again, reading the graph left to right, follow that line. If the line is going up, that vertical line, then that graph is increasing. So a graph that is increasing goes up to the left, to the right, as you're reading from left to right. Okay, let's look at another graph. We're going to again draw a positive y-axis, a positive x-axis. In this case, we're going to have a line that when you read it from left to right, you'll see that that line goes down to the right. And when a function goes down to the right when reading from left to right, that function is decreasing. So a function decreases if a graph goes down to the right. Lastly, constant functions are functions that are showing a flat line. When a function is constant, it means that we are going to have the same x values for, or sorry, we're going to have the same y values for a bunch of different x values. So a constant function is shown when you have a flat line. So remember, the key to identifying whether a function is increasing, decreasing, or is constant is to remember to read the graph moving from left to right, just like you would read lines in a text. Now you may be asked the question to state the intervals on which a function is increasing, decreasing, or is constant. So again, we're going to read functions moving from the farthest left over to the farthest right. So you can see here I have my vertical line, and looking at this function line, you can see that it only ever passes this vertical line at any given point just in one place. So this is a function. If it were to intercept this line in two or more places, then we would know that this was we would only be able to call this a relation and not a function. But this one for sure is both a relation and a function. So always remembering to read it from left to right. Let's start here at the negative infinity end of the x-axis. And from this point here all the way up to this point, you can see that that graph is going up as we move from left to right until we get about here. And then you start seeing that the graph takes a downturn. So this is going to be my first interval. My first interval on when it's increasing is going to be negative infinity to negative 1. My graph is going to be increasing. And you can see that I'm doing this in terms of my x values. Intervals are always described by the domain of x. So we're only interested in the domain of x for our intervals in terms of whether a function is increasing, decreasing, or remaining constant. So only looking at those x values. Next we have, you can see that from negative 1 to positive 1, my graph is decreasing. So that interval went from -1 to +1. I have decreasing. You can see here that I'm also using round brackets because -1 is being included in both increasing and decreasing. So I don't want to use a square bracket because that doesn't make sense here. That -1 is included in both the increasing and decreasing. And then next, after from +1 onward, the graph starts going up again. And it's going to keep on going in terms of this. So lastly, it's increasing again on from +1 to +3. But as I said, it's going to keep on going, especially if I put an arrow there. There we go, to positive infinity, and we always close infinity with round brackets. So we only use square brackets if data is distinctly included in one of those intervals. So if it's only found in one of the intervals and not another, then you can use square brackets. Otherwise, you want to use round brackets. And again, always read your graph, moving from left to right. And that will help you decide whether you're looking at increasing or decreasing or staying the same. Let's look at another example. Here we have another function drawn on the graph, and we're asked to give the intervals in which this graph is increasing, decreasing, and constant. So I always like to draw in my vertical line so that I can read going from left to right. So starting at, and remember we always set our domain in, we always set our intervals in terms of the domain of x. So starting at the -infinity end of the x domain, and then moving to the right, you can see that our graph increases to about -2. So I'm going to say that my graph goes from -infinity, and I'm doing a round bracket because we always enclose infinity with round brackets, to -2. And I'm going to close that with a round bracket because my next interval starts with -2. So my next interval is a flat line going from -2 over to +3. That means that we have a constant interval from -2 to +3. So that's where my function is positive, or my graph is positive. And then lastly, from +3 going to positive infinity, or actually in this case we have a dot, we have a finish point. And because we have an end point, then we decrease it from +3 to an 8, and it's a solid +8 because of that finishing point. So where my line here doesn't have a point, it has I'm going to put an arrow there. This here actually is a hard stop. It's a hard point, and because it's a hard point, then I have it decreasing on +8, and that +8 is a hard point, so I'm going to make sure that I put a square bracket for that. So far we've looked at different properties of functions. We looked at when functions increase, decrease, and remain constant. We've looked at when functions have x-intercepts and y-intercepts, so in terms of where they cross the x-axis and the y-axis. We've even looked at zeros of functions, which is another way of talking about x-intercepts. Now what I want to talk about is relative maximums and minimums in terms of a graph of a function. Now a maximum point is a relative maximum point. Looking at this function, you can see that they have both ends are going in different directions. We have the start of the graph, which is right here, which shows that it's going to go on forever, and we have the other end of the graph, which shows that it's going to go on forever in the positive direction. So going on forever in the negative direction, going on forever in the positive direction. And even though I have this pointing down, you remember that we are always reading from left to right. So the graph actually increases at this first part of the interval, then it decreases in the middle, and then it increases at the end, and it increases, keeps on going. So we have maximum at the positive infinity end, which means that we have the highest y value, highest positive at the positive infinity, and we have a minimum, the lowest minimum is going to be at the negative infinity range. But in between we have something called a relative maximum and a relative minimum. The relative maximum in this case is going to be right here, and the relative minimum is going to be right here, and we can identify those. The relative maximum is going to be when x is equal to -1, because that's our point here. And our maximum for our y value, I'm going to say it's around positive 2.5. So we have a relative maximum at the coordinate pair of -1, positive 2.5. And our minimum is when x is equal to +1. And again, that's going to be around the -2.5 mark. So at +1, -2.5, this graph has a relative minimum. And we talk about it being relative only because we do have these greater minimums and maximums, but because they are approaching positive and negative infinity, you can't pinpoint exactly what those are, so we call these relative maximum and minimum points. Now you can see that you can have more than one maximum point. So here we have two functions. In this function, I've got a relative minimum and two relative maximums. And in this one here, I have a relative minimum and a maximum. So you don't always just have one maximum and one minimum. You can have more than one of each. The next concept we're going to look at is describing functions in terms of being odd or being even. Functions that are even or odd have lines of symmetry. So for instance, in this first example here, if you look at the y-axis as the line of symmetry, you can see that the one side of the graph is reflected over the y-axis. So we have a reflection going on here. Imagine y to be the mirror line. In this example here, we have the two lines of reflection. First of all, the graph is reflected over the x-axis, and then again over the y-axis to get the mirror image. So we have two lines of reflection here. Whenever there are reflection lines or lines of symmetry, we can describe functions in terms of being even or in terms of being odd. Now an even function is going to have the y-axis as your line of symmetry, and there's only going to be one reflection happening. But when you have an odd function, what's happening is that you're going to get a reflection over the y-axis, whoops, like that, but then it's also going to flip over the x-axis, so you'll have a double reflection happening when you have an odd function. And again, even functions have that single reflection. So single reflection, you have an even function. Double reflection, you have an odd function. When you're identifying equations of functions as being either even or odd, it's great if you can graph them and look for those lines of symmetry or reflections. However, you don't have to graph an equation to find out if it's even or odd. How you test functions without graphs and lines of symmetry is by substituting -x in for x and seeing what the resulting function gives you. So for instance, in this first function of 3x to the power of 2 plus 8, what we're going to do is substitute -x into the function for x. So you can see we put -x in the function. So negative x goes in for x, and we get negative x squared gives us x squared. So 3 times negative x squared gives us 3x squared. So here the negative x gets, or the negative gets canceled out because we are squaring it. So we get 3x squared plus 8 as the answer when we substitute negative x in for x. Now if you notice, there's no difference when we do that. We end up with the same function. Even though we substitute negative x in for x, we still get the same function afterwards. And when that happens, that's called an even function, and you are going to get a graph that has a single line of symmetry. So even functions are when you substitute negative x into the function and you still get the original function. Odd functions are when you substitute negative x in, and instead of getting the original function, you get its negative form. So let's look at x to the power of 5 minus 4x. We're going to substitute negative x in for x, so we get negative x all to the power of 5 minus 4 times negative x. That's going to give us negative x to the power of 5 plus 4x. And comparing this final equation to the original equation, you can see that all the signs changed. We went from positive x to the power of 5 to negative x to the power of 5. We went from negative 4x to positive 4x. So what happens is that when we substitute negative x in for x, it changes all the signs for our function. So this is an example of an odd function. Now, if you substitute negative x in for x for an equation, and the result is that you get an equation that isn't the same as the original, and also you don't get a change in all the signs, then you have a function that is neither even or odd. And all that means is that there aren't any lines of symmetry for that function. So as you can see here, we substitute negative x in for x for the equation 2x squared minus x minus 1, and the resulting equation that we get is 2x to the power of 2 plus x minus 1, and that does not match the original equation, but it also does not match when you have a negative function. So in this example, you have neither an odd or even function, which again, that just means that you don't have any reflection when you graph this function. The last part of this section is looking at piecewise function. And a piecewise function is a function that is defined by two or more equations over a specific domain. So it's an interesting type of function because, as you can see here, there's actually two equations that describe the same function, except that each of the equations are for a particular domain of x. So in this case, we have the function of t is either equal to 20 when the x domain falls between 0 and 60. Otherwise, the function is described using this equation if t is greater than 60. So when you're evaluating a function like this, a piecewise function, you're going to look at what the x value is. So in this case, when you want to evaluate the function when x is equal to 40, you choose the equation depending on the domain that it describes. So 40 lies within this domain here. So that means that when we evaluate that function, so the function of c when x is equal to 40, that's going to lie within this domain, so it equals 20, following this piecewise function. If we are looking at an x value, or a t value I should say in this case, because we're looking at t, then t is greater than 60, so that means it lies within this domain. T is greater than 60, so when we evaluate it, we are going to use that second equation of t minus 60 to evaluate, because again 80 falls within that t is greater than 60. So we have 20, 0.4, 80 minus 60, 20 plus 0.4, and 80 minus 60 is 20 there. And then 0.4 times 20 plus 20 gives us 28. So when x is equal, or sorry, when t is equal to 80, it's going to, the function is going to evaluate that x value, or that t value, as equal to 28. And the last part of this section is graphing a piecewise function. Given the function, can you graph it? So first of all, the piecewise function that they give you is the function of x is equal to 3 when the domain is less than or equal to -1, and the function of x is going to be x minus 2 when the domain of x is greater than -1. So the first thing you want to do is set up two tables of values. One table of value is going to describe when x is less than or equal to -1, and the other table is going to describe the x values when x is greater than -1. Remember, we always set our x values because that is the independent variable. So looking at this first one here, when x is less than and equal to -1, I'm going to set -1 up and then do some numbers below that. So I'm going to do -2 and -3. The equation that I'm going to use for these numbers are going to be that first equation, f of x is equal to 3, because that's going to be what the equation is when my x values lie within this domain, and they all happen to be equal to 3. So my points that I'm going to graph are going to be -1 and 3, -2 and 3, and -3 and 3. And you can see that I've graphed those here. So it's actually a constant part of that function, and because it goes on towards the negative infinity, I can also put an arrow here. My next part of my function is when my domain is greater than -1. So when my domain is greater than -1, I'm going to have -1, 0, +1, and I could go more than that, but I think this will give me a good idea of the direction of my graph. But this time I have to use the equation x minus 2. So I'm going to input -1 in for x, and I get -1 subtract 2 is -3. Then 0 in for x gives me 0, minus 2 gives me -2, and 1 in for x, 1 minus 2 gives me -1. This gives me the points -1, -3, 0 and -2, and 1 and -1. Now, -1, an x value of -1, you can see that it's included in both. So for this one, it's only, included for this first one. In this second one, it just says that x is greater than -1. So I'm going to put a circle here, an empty circle, just to show that I start at -1, but it's actually not included. And then I'm going to graph my points, and then it does go off into positive infinity because I could have kept going here with my x values. So graphing piecewise functions, you are going to get different lines, different curves possibly, depending on what your equations are, and you are always going to set your independent x value depending on what the domains that are listed for that piecewise function. So that's it for this section 2.3. Next up we have section 2.4. Thanks for watching.